Welcome to the next lecture in the last week of the course Basics of Mechanical Engineering 2. We are discussing Introduction to Sustainable Manufacturing in this week. This lecture would be focused on life cycle assessment. I gave you an introduction to what is sustainable engineering, what is sustainable manufacturing, how is green manufacturing part of the overall sustainable manufacturing, and what are its components and major drivers. In this lecture, I will walk you through the life cycle assessment, phases, elements and steps or stages through which we conduct it. The four key phases of life cycle assessment we will see. Then we will see what are inputs, system boundaries and output, impact categories and some examples of life cycle assessment, tools and implementation strategies. We will talk about recent soft tools which are available, certain challenges in collecting data, in accessing data, in understanding the impact that we will see, and how is green manufacturing connected to life cycle assessment and what are various strategies nowadays being followed in green manufacturing. Then we will have a quick glance over what is unit manufacturing process as a part of the overall manufacturing system. When we go to the basic micro level or unit level system, so what is that? We will try to see an introduction to this, examples, classification of unit manufacturing process, and how do we use the different classification, different parameters which are there in unit manufacturing process to optimize. And I will show you the references. Life cycle assessment. Life cycle assessment systematically evaluates the environmental impact of a product, process or service across its life cycle, measuring resource use, energy consumption, emissions, waste. So these are all factors which are made. Resource use, that could be energy consumption, that could be emissions, or that could be waste. It plays a crucial role in eco design, product optimization, regulatory compliance, helping industries and policymakers to minimize environmental footprints. Advances in AI, big data, cloud computing has enhanced its accuracy, making LCA a vital tool for sustainable development. As I told you in the previous lecture as well, there are certain tools, certain companies which are working exclusively on life cycle assessment. Life cycle assessment is something when we talk about cradle to grave. You see here energy resources, material resources and water resources are input to a system. These are inputs. And this is our system, or I would say the overall processing happens here. This is the processing where it happens. This is the block where processing happens. There are certain sub blocks here. There are production of fuels, production of electricity, water supply, byproducts. So this is extraction. Extraction of, I would say, RM, that is raw material. And then comes production of materials, production of products, construction and refurbishment, use and maintenance and demolition. Out of this, we generate waste and deposition. These are downstream activities, and these emissions goes to air, to water and to land, which I would like to put it as cradle to grave. When I say extraction of the raw material, extraction of aluminium, aluminium is extracted as an ore. Then by distillation methods, the ore is extracted, pure metal is taken out of it, different grades of aluminium are extracted, that is the extraction of metal. Then this aluminium goes to different kinds of industries for manufacturing, for utensils, for the components of the automobiles or so, these are taken. Then duralumin, for example, is used for aircraft manufacturing. So those are all taken. Then comes the building product part, where we treat the materials as per a requirement, certain heat treatment metal. Aluminium is mixed with other metal metals to develop alloys. Those alloys are used here, and manufacturing of the products is the major concern of our course here. When manufacturing is happening, all the processes that we have studied in the previous weeks, we use those here. And then construction, refurbishment, use and maintenance, demolition. I'll come to this one by one. When I talk about cradle to grave, in between we have multiple stop points. For example, here it could be a stop point, here it could be a stop point, here could be a stop point. We call it as stop point or halt points. We call it as gate. So what happens in the cradle, I would say it is the very beginning, the raw material. And grave is finally the end of life. End of life, that is disposal. In between we can have production, I will just production here, or I can have the use. Production when the product is produced, use is when the product is being used by the user. So these are the gates. This is a gate, this is a gate. From cradle to gate, or gate to grave, or from maybe gate 1 to gate 2, gate 2 to gate 3, certain gates are there, or certain steps are there. In between we can put our scope of the life cycle assessment, what kind of assessment we wish to do. So now let me see, in the building of the product, what are these 5 major stages here. First is production of materials. For materials like aggregates, one of the main effects will be getting the raw materials. For more highly treated materials, on the other hand, production effects are more likely to be the main effect. Manufacturing, which is our major concern, this is making things. This has the biggest effect on the world, because this is something that we are doing major of the time, especially if a lot of energy is needed to make metals or cement. Refurbishment and repair, energy and water are used during building and fixing things up. It is not only manufacturing, post-manufacturing refurbishment also happens. So based upon the IGT BIS standards, which is the Indian standards, final report says that 10 to 15% of the materials sent to a building site are thrown away. Here we are talking about a construction site. Just for an example, they say 10 to 15% of the material goes away. 40% of the food is wasted, whatever is produced. So these are all different streams which I am talking about, but we are majorly focusing on the manufacturing. Then comes use and maintenance. These tasks makes up to 45% of the contractor's output. We are talking about the construction only. Yearly turnover, which means that a lot of effects of mining, manufacturing are likely to happen to materials used during maintenance. When I say use, a car is manufactured, a scooter is manufactured. That is manufactured. Before manufacturing, raw materials comes from different parts, plastic material, metals, and there are certain nuts and bolts are developed, ancillary units provide those to us. And finally, maybe car is manufactured. This car is used by the person. During use as well, there is a lot of data. So that use and maintenance part is being discussed here. Then comes demolition or disposal. Demolition in the case of buildings, disposal in the case of any of the products that we can talk about. Some things can't be used again or recycled, so they end up in dumps and trash. End of life problems are now being thought about from a very beginning of a product's development, so that it can be easily taken apart and used again or recycled when its time has come. So the point is, we need to have a planning here itself. I will call it as planning, or I will call it as the design that you do. So design for manufacturing. Design for manufacturing is known as DFM. That is, if you are designing a product, if I am designing this stylus, if I am designing this mouse, it has to be designed in a way so that it could be manufactured. The shape could be properly developed through the process that we are using. We might be using injection molding, we might be using some CNC machines to develop or to cut the metal materials. So designs has to be made so that it could be manufactured. Also, when the manufacturing has happened or manufacturing is going to happen, we also need to see the repair and maintenance should be taken care of. That means the design that you are developing or making should be able to be maintained. So design for maintenance. This is known as DFMN, design for maintenance. You get a car repaired as a preventive maintenance each 3 months or at each 10,000 kilometers. That is, the design has been made for maintenance, and overhauling happens maybe once in 5 years. That is also designed for maintenance. Once in 5 years this overhauling will happen, and this regular preventive maintenance would happen each 3 months. It is designed for maintenance. Nowadays, when we talk about life cycle assessment, this all designs are there. Design for assembly is also in between there. That is, the component should be able to be assembled and disassembled whenever required. The new term that has come nowadays is design for environment. Design for environment I will call it DFV, which means the components that could be recycled, that should be more put there. The components that could be reused could also be put there, so that they can taken from that product and put into the other product for you. For example, nuts and bolts, those could be reused in some other parts. Design for environment, which means the disposal or the final end of life of the product should be planned in the beginning only. What part would go to the solid waste, what part would go to the liquid waste or so. This is design for environment. So this is what life cycle assessment helps us to understand. So this is a more detailed figure about cradle to grave life cycle assessment. This is production phase, when raw material extraction, component production, vehicle production. This is about the vehicle production now. It has been taken from a study which is talking about electric motor scooter development. Then come use phase, that is wheel to wheel, fuel, electricity demand, vehicle emissions. So this is the production phase which I am talking about, manufacturing. And this is a use phase when it has reached the customer. That is, scooter is being used by the customer. Finally, it goes to the end of life. So this is cradle to grave. Here we have extraction of raw materials even before the manufacturing that we have seen in the previous illustration. In this case, some data points that we can see from this study, the base case, you can see there is a legend available. This is production, in transport, charging, battery swapping, end of life. Majorly, you can see the environmental impacts which had been calculated using some of the tools of life cycle assessment is in either production, that is dark blue, or it is in battery swapping. That is in use case, this is battery, that is written here, battery swapping, and majorly it is production. Transportation is very minimal, just between production and use there could be transportation, and you can see end of life is also a small end edge. You can see this is end of life, which means majorly the significant contributor to the life cycle impact is production and the usage, that is battery swapping. In this case, the certain pointers they have given is base case, shorter lifetime, 40 kilometers range, then longer range, that is 66% battery swapping frequency, solar power for charging, battery swapping for e-vans, etc. So this is the data that is taken from one of the studies. And the output is given in grams of carbon dioxide equivalent per kilometer. This is carbon footprint. Now let me talk about key phases of life cycle assessment. First and the foremost phase is definition and scope. Life cycle assessment systematically evaluates the environmental impact of a product or a service throughout its entire life, covering production, distribution, usage, disposal, guided by ISO 14040 and 14044 standards. When I say life cycle is from cradle to grave, that is from extraction of raw material, to the treatment of the raw material, that is furtherly to be used in manufacturing, then from manufacturing to marketing, from marketing to customers, that is a use phase, from use phase to reuse phase, then from there it goes to disposal. In between, we can define the scope. My scope or definition of the life cycle assessment that I'm going to do the study on is only between the raw materials to manufacturing, is only within manufacturing, or is between from manufacturing to marketing. It could be majorly transportation, manufacturing to marketing, or between marketing to the customer, or during the use phase. This is how do we define the scope, what is our definition, what are we going to be focused upon. That is three factors: energy, emissions, material. What are we going to focus? 1, 2, 3. I'm going to only talk about energy being used in manufacturing. I'm going to only talk about the water consumption that is there in manufacturing. We have to define the scope of the life cycle assessment first. Then comes inventory analysis. It involves collecting data on material and energy flows, documenting inputs, that is raw material, energy, and outputs, that is emissions, waste, to assess environmental burdens. I will talk about some tools or equipment or gadgets used to measure the energy consumption or the inputs and outputs in machining. That is the next lecture, green machining. Now, these are to be captured, that is inventory analysis. This is not inventory, that is raw material inventory we are talking about. When I say inventory, it is life cycle inventory I am talking about. This is life cycle inventory. Life cycle inventory, which talks about these inputs, raw materials and energy, and outputs, it is emissions and waste. Then is impact assessment. This phase classifies and quantifies environmental impact, linking resource use and emissions to categories like climate change, water depletion, toxicity to evaluate significance. Now, energy, emissions, material, whatever is there in a scope, that scope is being evaluated and impact assessment is being taken here. Then comes interpretation and optimization, that the results are analyzed for accuracy and used to identify improvements, ensuring minimal environmental impact while preventing burden shifting across life cycle stages or impact categories. So, what essentially happens when we rate our factory based upon the greenness that is required, based upon the sustainability level that is required, if I say I just color my factory between red to green, red is the most non-green factory, green is completely green, completely net zero factory. In between I can have the range of colors, red, orange, yellow, blue, green, etc. Now I have to first put, based upon the certain criteria, where does my present condition lie, what is the current scenario. Suppose if I lie at orange, from orange if I can move to yellow, that is my impact improvement, that is interpretation and optimization, that one step I can go ahead. So there are certain ways to do it, there are certain courses which are there on NPTEL as well, you can visit those and try to understand more about life cycle assessment. Here I will basically focus upon mechanical engineering only. Life cycle sustainable assessment, just to put a relationship, for the complete sustainable assessment, it is sum of the life cycle assessment plus life cycle costing plus social life cycle assessment. These are different components that you can see. Life cycle costing is talking about the cost of ownership. Cost of ownership, that I will talk in the last lecture when I will talk about the metrics of life cycle assessment or metrics of sustainable manufacturing. What is cost of ownership? It is life cycle costing. And what is social life cycle assessment? This I will also talk about in the last lecture. So total life cycle sustainable assessment is an aggregate of all these. Again, the inputs are energy, material, ancillary and others. There are raw materials, manufacturing, distribution, use phase, end of life, and outputs could be emissions to air, water, land, waste and others. Certain impact categories, that when we are measuring the impact, to what level are we going to report it? First is global warming potential, GWP. The most widely adopted metric for analyzing environmental impact is GWP. It measures the impact of a product's greenhouse gases emissions on climate change expressed in carbon dioxide equivalents. When carbon dioxide equivalent, when we say the measurement base is carbon dioxide. If I say methane is also generated, if I say sulfur dioxide is also generated, methane, if 1 kg of methane is equivalent to what amount of carbon dioxide that is taken, that is what is normalized based upon the carbon dioxide. So it is carbon dioxide equivalent that is taken as the carbon footprint. Ozone depletion potential, ODP, this assesses the impact of chemicals like chlorofluorocarbons on the depletion of ozone layer, which shields Earth from harmful UV radiation. Acidification potential evaluates the potential of emissions such as sulfur dioxide, nitrogen oxides to cause acid rain, affecting ecosystems and soil and water. Eutrophication potential, this measures the impact of nutrient emissions like nitrogen and phosphorus on water bodies, leading to algal blooms and oxygen depletion. Some other impact categories are photochemical ozone creating potential, that is POCP, that is also known as smoke formation potential. This category assesses the impact of volatile organic compounds, that is VOC and nitrogen oxides in forming ground level ozone. Resource depletion, that examines the consumption of a non-renewable resources such as fossil fuels, minerals and potential for scarcity and economic impacts. Ecotoxicity is one that assesses the potential harmful chemicals and pollutants released during the product's life cycle on ecosystem and biodiversity. LCA tools and implementation strategies, multiple tools are now available in the market. There are certain software which are available, which are exclusively working on assessment of the life, that is assessment of life cycle of the product, of the process, of the overall factory, or maybe the kind of the sector if you pick. For example, if you try to pick the water intensive factor, for example, leather industry. If you wish to pick the energy intensive factor, that is manufacturing of metals industry. Then if you wish to pick maybe agriculture industry, for those different software systems are available. And there are also databases which are available. For example, Proves. Proves provides you the database. You might have to procure the database to have an assessment to what you wish to do. There are certain LCA software selections that you could do. There are tools like SEMA Pro, Gabi, OpenLCA, which provide core LCA functions but require manual input. The AI-driven tools enhance automation and accuracy. Automation and accuracy, automating data collection reduces errors and improves assessment reliability. That is, we use Internet of Things and we put sensors to collect the data. Real-time analysis, while putting these sensors, you can also have an real-time analysis using the apps. That could be the Windows apps, that could be the Android apps, or it could be iOS apps. These helps us to have real-time data processing that supports better decision making across impact categories. Then we have advanced modeling. That is, robust modeling tools optimize sustainability strategies and product lifecycle. Whatever apps we develop, for example, Gabi is one of the software that is there. There is a GUI, graphical user interface. You input the data, at the back end some calculations is happening. Those calculations are the algorithms which we are talking about here in modeling. Those models also, you can develop your own models, develop your own apps. There are tools which helps you to put your own data here. But there are certain challenges when we talk about lifecycle assessment. Some of the challenges that I have listed here are data limitations and accuracy. Obtaining reliable data is difficult and inconsistencies in data sources can affect accuracy. Data, when we talk about secondary data, there are data sources like I talked about Proves. There is data available in Gabi. Secondary data, that is an existing data. There is a tool or a website called as EIOLCA. That is Economic Input Output Lifecycle Assessment. They have the data. But these available data sets or database is sometimes not exactly meeting the requirements that we have. For that, we have to conduct our own experiments. That is, we need to collect the primary data. So for that, reliable data development or creation needs resources. That is, it needs money, it needs manpower, and it needs time to collect the data. So to collect the exact data, it is very tedious job sometimes. That is one of the challenges. Then high time and cost requirements, as I have mentioned here, the resources. The conducting of full lifecycle assessment is expensive and time consuming, making it challenging for small businesses. Complexity in system boundaries and impact assessment. System boundaries, that defining the boundaries and translating inventory data into actual environment data impacts is difficult and can lead to variations in results. Standardization and integration issues, that is differences in methodologies, uncertainty in results, difficulties in integrating LCA findings into decision making limits its effectiveness. Different kinds of tools if you keep using, or different kinds of the data collection methods are there, those are difficult to be confined to one specific decision. Aggregate data or specific unit process data, there are different ways to collect it, but we have to first define or plan what LCA scope we are going to do and what kind of impact we need to measure finally, then it is easy to do. Green manufacturing and LCA, if I try to have a amalgamation between them, you can see this, we are talking about a life cycle of equipment, this is life cycle of a product. These will two run as two gear wheels meshing together. So here we have the design of equipment, production, configuration, use and adaptation. Here also we have design, then production, then use and adaptation. These two go hand in hand, and what are the things that come together? Let me try to see some strategies here. Green manufacturing and life cycle assessment strategies. Strategies for sustainable manufacturing extend beyond environmental impact to broader industrial practices. To manage emissions and waste, three main strategies exist, that is pollution prevention, end of pipe control, environmental restoration. This is the table that gives you the intensity of articulated industrial robo, in which you can see the material is steel, stainless steel, copper, aluminum, PVC, or electronic materials are there. The amount of material used is given here for specific robo that is being manufactured. This is also taken from a study here. And you can see the intensity of resources which are there. You can see the abiotic material that is given here in kgs. You can see water that is given here in kgs. You can see air that is given here in kgs. So these are some examples. When we collect the data, this kind of the tabular form of the data you get. From here, you can see in the terms of emissions in air, in water, or in abiotic material, what are the material inputs. Now to talk about these three main strategies, pollution, end of pipe, and environment, let me give you a brief introduction. Pollution prevention, controlling emissions before and during production by reducing material and energy use, using environmentally friendly materials. This I will talk in the next lecture for a specific green machining case. This approach is cost effective and impactful, minimizing waste treatment needs. End of pipe control. When I say end of pipe means between cradle to grave, how are the material systems flowing? So managing emissions and waste after generation but before release through recycling, collection and filtration, waste treatment. Recycling is one, as I took an example of aluminium material which goes in the car and it is further recycled when the car, after the use phase, the overall dismantling happens. This material could be reused or it could be recycled, and it could be again be converted using the casting processes or various processes that we have studied into the usable form. Now collection and filtration. Collection and filtration, when I say for example, I am talking about a big product, a car. When it will be dismantled completely after the reuse phases, the nuts and bolts, the metal materials, in metals as well, aluminium, SS, all different components are segregated. That is collection and filtration. Then waste treatment, material that cannot be used at all, that is going into disposal, that is waste treatment. This is useful for retrofitting but less effective than pollution prevention method, as it manages rather than reducing waste. So pollution prevention is the first priority. Then is end of pipe control that we can do. Then even if end of pipe control is somewhat restricted, we can at least have environmental restoration. Addressing environmental damage after waste releases through hazardous waste management, site restoration, limited water and air treatment, costly and less effective, often last resort when system fails. For example, NASA, while launching a rocket using tons of gallons of water, to have a restoration of it, they do certain endeavors for water treatment, for water collection, etc. All those things are taken care of. Now, cost effectiveness in comparison between the criteria and optimizing manufacturing through pollution prevention is very important. When I say cost effectiveness, costs rise while effectiveness declines when shifting from pollution prevention to environmental restoration. Pollution prevention offers best balance of cost and impact reduction. Optimizing manufacturing through pollution prevention, focusing on pre-manufacturing stages, minimizes waste and emissions from the outset. Identifying and eliminating environmental impacts early makes it the most efficient and economical strategies. That is, when we have eliminated in the design phase, that is, we are majorly focusing on prevention only. Prevention is better than cure. This phrase always holds true. Let me now have quick introduction to unit manufacturing process. Manufacturing is a process of converting raw materials into finished products, which we all know, with specified shape, structure and properties. This transformation is achieved through various processes that apply mechanical, thermal, electrical, chemical energy to create control changes in the material. Modern manufacturing integrates designs, materials, engineering and process planning to ensure cost effectiveness, efficiency and sustainability. Why I am telling about manufacturing once again, because when manufacturing we will talk, there is specific unit, specific kind of the operations when we do. For example, you are doing turning operation, that is a machining operation, that comes as a unit process. For example, if you are doing casting, in casting you are specifically doing casting for a specific component. For example, you are doing a casting for a carburetor for a car. For that, casting is a unit manufacturing process. So unit manufacturing process is a fundamental operation. The word fundamental is very important here. It is a fundamental operation that adds value to raw materials by altering their shape, structure, properties. These processes are building blocks of production, and their integration forms complete manufacturing sequences, also known as process strings. So this is also known as line, or I will better call it as production line. Unit process is optimized when it delivers the required transformation in the most cost-effective manner while minimizing waste, energy consumption, and environmental impact. So that is, unit manufacturing process is the building block. If you try to work upon one block, if this saves energy, if this is replicated for each construction of a complete building, that building whole would be having the same equivalent percentage saving in the terms of any of the emissions, solid, water, etc. So to do this, we need to have certain sensor-based technology systems. So traditional sensor-based monitoring system manufacturing has relied on accounting-based tracking and theoretical energy estimates, both of which lack accuracy and granularity. So nowadays, software-driven automated sensor data reasoning are there, which enables precise decision-making across multiple temporal levels. So you can see at a production planning level, at a macro planning level, then micro planning level, and process control. From the process control itself, if I try to do something here, this will reflect up, and finally production planning has to be done in such a way. A smart manufacturing monitoring system is one which integrates real-time data analytics, automation, and interoperability to optimize efficiency, detect anomalies, and enhance decision-making in manufacturing. There are certain examples of unit manufacturing. As I took the example of machining. In machining, an example could be lathe, workpiece is bar material, type of tooling is single point, typical interface across the tooling is cutting fluid, primary work zone mechanism is deformation and fracture. Similarly, for other processes, which are unit processes, for surface modification, for casting, for forging, for powder compaction, for fusion arc welding, there are certain examples. And let me take just for example of for forging. The equipment is press, the work material is preform, the typical tooling is a die that converts it into the desired shape, typical interface to the material is lubricant, and what is the primary work zone or mechanism that is here? It is deformation that happens. So these are certain examples of the unit manufacturing processes. These are all unit manufacturing processes given in the first column. Now, unit manufacturing processes and process optimization. There are families of unit manufacturing processes. For example, there are unit manufacturing processes which work on mass change, then phase change, structure change, deformation, consolidation. I'll talk about all of these, and these are further also optimized based upon the kind of the material that we are using. Material could be metals, composites, ceramics, or maybe ceramic matrix composites, polymers, or maybe polymer matrices as well. Then there are certain different process components that we are using. For example, workpiece material, equipment, work zone, interface tooling. So what specifically are we going to focus upon when we are talking about our life cycle assessment goal? We can pick out of these. Now let me try to see the classification of unit manufacturing processes based upon the families which I showed you in the previous illustration here. Unit manufacturing processes can be categorized into 5 major families based on their physical transformation methods. Number 1 is mass change processes. These processes add or remove material using mechanical, electrical, or chemical means. Certain examples could be machining, grinding, electrochemical machining, etc. Then comes phase change. When I say phase change, that means we will heat the metal above its critical temperature. So that is the processes that involve solidification from liquid or vapor phases. For example, casting, injection molding, metal infiltration. Then comes structure change processes only. When we alter the microstructure, that is the heat treatment processes when we talk about, those comes under the structure change processes. These processes alter materials microstructure or to enhance mechanical properties. For example, heat treatment, surface hardening, annealing, etc. Then comes deformation processes. As I have talked about, metal deformation happens. Here we have materials shape change without altering its mass or composition, that is rolling, forging, deep drawing, etc. Then comes consolidation processes. These processes combine materials into a single component, for example, powder metallurgy, composite pressing, welding, brazing. Next comes union manufacturing processes optimization. Optimization goals, that is, reduce energy consumption, material waste and labor, maximize efficiency and product quality. When I will talk about green machining in the next lecture, I will also talk about the importance of optimization. When I say optimization, you have to pick out of the range of the materials available, out of the range of the different kinds of the processes, out of the range of the different kinds of the parameters in the overall system, what we are going to work. That is, I am going to define my goal and scope of life cycle assessment. For example, in this illustration, I have marked now 3 different boxes here. You can say I have picked deformation, equipment and metals. When I say deformation, that means out of all the unit process families, I will only pick deformation. That is, I am talking about forging, right? Then forging of only metals. For example, I will talk forging of mild steel. Then when I am talking about deformation and metals deformation, out of the workpiece material work zone interface, what I am going to focus about? I am going to talk about the forging equipment. I will talk about forging press. So this is, I am defining my goal or scope of the life cycle assessment. That is, I am trying to pick a specific kind of an equipment, deformation family, and I am going to pick material, that is metals only. Process is equipment here. Now, I have to pick those which are more significantly affecting my overall life cycle of the product. Equipment energy, energy being used in work material, energy being used in work zone. Equipment will occupy maximum energy. If I am trying to focus upon energy, I might pick these. I might pick some other depending upon what is my scope of study. So this is, we try to work upon the optimization. Then key focus area of optimization are enhancing productivity through innovative methods, improve sustainability by integrating eco-friendly processes, utilize advanced materials and automation technologies. Industrial impact of optimization is increased cost effectiveness and reliability, improve environmental sustainability. It drives in advancements in modern manufacturing. Again, talking about the 5 primary components: equipment, the machinery used to apply energy and force, workpiece material, the raw material undergoing transformation, tooling, tools that interact with the workpiece, interface, the medium that facilitates energy transfer, that could be lubricants, coolants, etc., and work zone mechanism, that is the physical process altering the workpiece. That could be deformation, solidification, diffusion, or anything like this. Now, let me try to see the boundaries of a unit manufacturing process. When I talk about a unit manufacturing process, if I am talking about suppose only machining, machining is typically material removal. In material removal, there are certain boundaries. In material removal, we have associated boundaries. We have material production that comes as input, tooling preparation, single point cutting tool or any multi-edge cutting tool that comes for the material removal. Then we have machine tools that comes an interaction. Then we have cutting fluid that goes inside and outside. And I will talk about the methods such as minimum quantity lubrication. The only input is here. There is no recycling of fluid, cutting fluid here. Then we have facility inputs, that is lighting, heating, ventilating systems, etc. that comes here. Then comes part cleaning, that is dirty parts goes out and cutting fluids goes out. So here we have the scrap or the emissions there. These further, each of them have their own interaction. For example, if I only talk about machine tool, machine tool has in itself the parts of machine tool, the lubricant of the machine tool, the energy that is being consumed in machine tool, that is variable. They spent lubricants and parts. So these are all interactions or the boundaries of a specific kind of a unit manufacturing process if we try to focus upon. Let me try to see each of the boundary boxes one by one. Raw material extraction and preparation. Inputs could be ore, raw stock, near net shape parts. Processes could be materials production. Outputs are usable tooling, processed materials. Tooling, machine preparation. Inputs are tooling, fixtures, tool holders. Processes are tooling preparation, machine tool construction and maintenance. Outputs are ready to use machine tools. Cutting fluid preparation. Inputs are water, additives, cutting oil. Processes are cutting fluid preparation. Output here is clean cutting fluid. Energy supply and facility operations. Inputs, electricity, heating, ventilating, air conditioning, compressors, lighting. I'm talking about facility, that is factory facility now. Processes are facility operations, machine power supply. Outputs are heat and spent energy. Material removal, that is the core machining process. Here we have input as energy, machine tools, clean cutting fluid, raw material. Processes could be cutting, milling, drilling, grinding, anything. Outputs are the dirty parts, spent cutting fluid, scraps and chips. Part cleaning and finishing. Inputs are cleaner, water and energy. Processes are part cleaning. We get as an output clean parts, spent cleaner, wastewater and soil. Next and the last is waste management and recycling. In this, the inputs are spent lubricant, contaminated leak cutting fluid, scraps and chips. Processes are waste treatment, recycling, reuse of materials. This is very important here. Outputs are recycled material, properly disposed waste. So sustainability and green manufacturing considerations, just to summarize, we have to focus upon energy efficiency, that is reduce energy consumption in machines and heating ventilator systems. Then waste reduction, recycling and reusing spent fluids and metal chips. Then process optimization, that is minimizing raw material waste by adopting near net ship manufacturing, and eco-friendly coolants and lubricants using bio-based or recycled cutting fluids. I'll try to focus or talk about these in the next lecture when I will talk about green machining, and there are certain references from which all this material is taken. With this, I'm closing this lecture. In the next lecture, I will talk about green machining, and in the last lecture of this week or in this course, I will talk about certain metrics of sustainability. Thank you.